It's a pleasure to introduce George, who came from the furthest away. He wants to talk about product vessels and trivial resulting spaces with applications to nonlinear approximation.
Okay.
George.
Before I start, I want to say that I'm really happy to be here among friends. The good news is the last talk of the day of the workshop, so you can sleep after that. The bad thing is that game cards playing against Tennessee in an hour, and most likely we're going to lose. So anyway, I want to say a few words about Wolfgang and Penso. I really feel privileged to be associated with you and to know you throughout the years. I remember I first met Wolfgang in the late 80s when Angela was here. She did the last part of her PhD here for 2 years, Angela Kuno. Yeah. And I was simultaneously here. And then, that was 89, 90, I think, something. Yeah. And then I met Penso later.
Oh, later?
We started collaborating at around 2000. We have more than 15 papers together. So it's... Anyway, I want to wish you a productive and happy life among friends and families.
Somehow you are always connected. When I think of the IMI,
we had good times here. Unfortunately, I don't have any stories to tell you about these guys. I have many stories about Ron if you want to tell you.
Some of which are true.
Yeah. Okay. Let me start. This is joint work with Penso and Nasos Georgiadis from Cyprus. So we started looking harmonic analysis from the point of view of multi-parameter theory, and we tried to see how this translates to what we know to the usual single parameter that we're used to, and to see what is the if someone tries to do nonlinear approximation, what is the effect of multi-parameter theory in nonlinear approximation? As you will see, we lose something. Okay, so this is the outline of my talk. I'm going to just refresh you a little bit in one parameter Fourier analysis. Then I will introduce somehow multi-parameter theory, go through. And then there's a standard program. We go through we find homogeneous Bessel and triple working spaces. We have to go through the decomposition. Then I will define wavelets. I will remind you what are the wavelets on these product spaces. And finally, I'm going to talk about nonlinear approximation, and we talk about direct and inverse theorems. Okay, that's the program basically. We're going to do nonlinear approximation with wavelets. That's why we need these 5 here, otherwise we wouldn't have inverse theorems. I mean, you can get direct theorems with frames, but not inverse theorems. That's the problem. Okay, so the main objective is to develop the theory of product Bessel of triple working spaces in the spirit of Fraser and Yaworth. Most of you are well aware of this. And then establish sharp Jackson-Bernstein estimates. Okay, let's go back now to the 70s. So the classical theory of Calderon-Zygmunt basically is centered around this maximal function, maximal operator, and its relationship to singular N-class operator. And the common thread between these is that this operator, the maximal operator, and the singular N-class operators, they commute with this usual one-parameter family of dilations. Now, the investigation of the boundness of Calderon-Zygmunt operators, it led naturally to the definition of Hardy spaces. Okay, I'm referring to one. So let me just remind you. The thing here is that the whole theory basically came from the weak L1 estimate. That's what was the important part. Now, let me just, okay, so for the definition of HP spaces, I'm using the definition that we're going to need is, we start with function phi, which is infinitely smooth. The integral is 1. It's not important for the integral to be 1. We don't want to be 0. And then we create this dilated version, okay? We dilate the function. And then here we take the HP function, the norm of the HP space is the supreme, the LP norm of the supreme of this average, maximal averaging. You see the difference between these two. This is a quantitative estimate, clearly a quantitative estimate. This is quantitative and qualitative, because once you have the absolute value outside, then zero moments are involved because you have cancellations there. So this is somehow different estimates. However, can we, Peter? Can we
move the mouse?
Oh, it's the mouse.
Actually, we use the mouse.
However, you can
Move it over. Move the mouse.
This is the mouse.
Yeah, but yeah.
Thank you.
Okay.
Oh.
No, when you go to full screen, this
Now
thing
move the
pops
mouse.
up.
View. Full screen.
Okay.
Okay.
However, these supremos are somehow controlled by the maximal function. So a lot of theorems here they went through the maximal function eventually. Now, let's assume that we want to have a parallel theory, an analogous theory, where instead of this family of dilations, we have two-parameter family of dilations. So let's say we have the space Rn1 times Rn2, and then we have these dilations. We have different dilations with respect to each coordinate. So these problems were studied a lot in the 80s. I will give you some references. And the natural operator which is associated with this dilation is the strong maximal operator. The strong maximal operator, things here are substantially different. For instance, first of all, the strong maximal operator, or as it called Zets and Marcinkiewicz, Zygmunt operator. So we take for each x, we take the average of the function, of the absolute value of the function over rectangles. Now, these are rectangles with sides parallel to the axis, or if you want, this is a cube. Q1 is a cube in the first space, and Q2 is a cube in the second space. So we have cubes of different size, but they are cubes. Now, this maximal operator is not weak L1, L1, for instance, anymore. It's not weak L1, L1. Also, the differentiation theorem, which means that if you take the average and that converges to the function almost everywhere, this doesn't hold. There's a counterexample by Sachs from 1934 that they have a function that this average they converge to infinity. So they don't have almost everywhere convergence.
What is the interest of it? Just to be exotic?
No. Hold on. Okay.
The fact that you take just two parameters, is it for the purpose of the presentation, or
What do we say?
why you just take I equal 1, 2? Could you have N1, N2, and D?
Here.
Yeah.
Yes, I can have more. I will tell you the difference.
But could you have just a general scaling matrix, a diagonal matrix?
Yes, but you want to have different. Yes, you could have, but different dilations. Okay.
Yeah. I mean, the point is, we're trying to understand, are you fixing delta 1 and delta 2?
No. Because they're not. I'm not fixing delta 1.
So this is overall rectangle, so
Yeah.
why do you introduce delta 1 and delta 2?
Yeah.
Independent.
It's independent. Yeah. This operator commutes with these dilations. That's what I'm saying. Okay.
And that delta 1, delta 2 corresponds to cubes of different sizes.
Yes. No, but this is independent of this. This is independent. This is dependent. Okay.
His notion of dilation is to dilate anyway.
You have so in your first page, I didn't ask the question, but on your first page, there's something called the grand maximal operator, which incorporates all the phi's.
No.
Yeah, of course.
Yes.
I mean, the Pfefferman's grand maximal.
Yes. Here. Yes.
You didn't use the Grand Max.
No, this is the definition.
1.5.
This is the definition. This is 1.5. This is the definition.
Yeah.
I understand,
And
you're
you
right.
have HP characters.
Yes, you have several. I mean, this is the one characterization we're going to use, but you have several equivalent characterizations. Okay, so let me say that if you want to study singular integral operators that commute with this dilations, this family of dilations, then you start studying these HP functions. So you have, so phi is on this space now, it's rapidly decreasing functions, test functions, the integral is 1. However, you have different dilations. You dilate differently in one variable and differently in the other variable. And then you have to take the supreme over the two different of T1 and T2. That's the multi-parameter Hardy spaces. And of course, the multi-parameter Hardy spaces are controlled, again with the same, are controlled by the strong maximal function, not by the maximal function anymore. Now, let me just say the multi-parameter field is not a simple extension of the one parameter. For instance, what I'm saying here is atomic decomposition does not hold in the usual sense. And there is a counter example of this by Carlson. Okay, let me just give you some references. I mean, the study of this space started, I guess, with this paper of Gandhi and Stein, 79. They used HP theory on the polydisk, so they did it on the cross product of two disks. And then Robert Pfefferman with Alice Chang, they had a series of papers. This one, and this one are, yes, they are very instructive. I mean, 2 and 5. And then you can see there are several papers on this subject. I mean, people studying work on this.
But Bobby is familiar with this stuff, I'm sure.
Bobby is familiar with maximal functions. Or, yes.
Bobby, do you have this in your book?
Strong maximal function.
Yeah.
You have the strong functional function. I think you have it.
Just
I think you have it.
maximum.
Yeah. Okay, so what we wanted to do, we wanted to see to extend this theory of Pfefferman, Alice Chang, of all these guys to the triple isomic space and to see what we get out of it. Now, we are going to do it in the cross product of two spaces, but of course you could have done it in more. Okay, there's a difference. I will tell you what will be the effect. Now, in homogeneous product, best of a triple isomic space appeared. You can find this by Schmeisser in the literature. These are the papers that we were able to find. Okay, so what I'm going to do now? I'm going to go through the theory. In parallel, I will introduce also the one dimension, the one parameter theory. And for those of you who haven't seen it, let me just say the dimensions of the space is irrelevant in this type of business. The number of parameters is relevant. The number of parameters. So the main developers of the triple isomic space, I would say the first one was Petrie. From Petrie started everything, and then Tabor and of course Fraser and Yaworth. But I believe that Petrie was the one who his book New Thoughts on Bessel Spaces is the Bible, I think, of this area. Okay, so the construction starts. Let me go through quickly with a function phi, which is on the Fourier of the time domain is supported between 1/2 and 2. It's positive, strictly positive on some subset of 2 of 1/2 2, and then we start creating these dilations. So the Bessel and the triple isomic spaces are basically measure smoothness, and as Kamen said yesterday, by playing with these indices, you can recover most, especially in the triple isomic space, you can recover most of the usual spaces. And of course, when P equals to Q, this is obvious that they are the same. It's important to notice that these are space of distributions, and they don't see polynomials, they don't recognize polynomials. And they shouldn't recognize polynomials because these are for certain variables here, for certain choice of the indices. These are the Sobolev space, and we know the Sobolev with the semi-norms, not with the norms. So and the polynomials are, the norm of polynomials is 0. Okay, so this is the one parameter theory. Now for the multi-parameter theory, what I first need to do is let me define a little bit the classes, the class of distribution of the test functions we are using. So the test functions basically are going to be smooth functions in both coordinates, infinitely smooth functions with both coordinates that decay almost exponentially, decay as fast as we want polynomially. Okay, and the dual of these functions is the space of tensor distributions. Now, actually, what we want to do, we want to work. Because as I told you, we're going to work with equivalent classes models of polynomials. We want the class of distributions to annihilate polynomials. So this is the dual. And so the dual space does not recognize polynomials because the test functions annihilate polynomials. So it's so this is the space of distributions. Okay,
so
now.
Really, all this formally, as infinity prime, Rn times Rn2 is the same as Rn.
I agree.
So there's no difference.
I agree.
The only difference is in
Yes.
that, your action on kind of tensor product spaces.
I agree.
That you have polynomials of then
that's
go
correct.
like that. That's the only thing.
That's correct. Yes.
Okay.
Okay.
That's going to lead to mixed smoothness.
Yes.
Does it?
Yes. Yeah. Exactly.
So
Exactly.
you are interested in mixed smoothness?
Yeah. Yes. So the definition of the space. So we get two functions, phi1 and phi2, that both satisfy these assumptions. Okay. One satisfies in Rn1, the second in Rn2, and we're going to take the cross products. Okay, we take so our smoothness now. Our best of trivial working space. The smoothness, we're going to have two indices for smoothness. One index is for each space, and here you notice that we sum up over nu here is over Z2 because nu is N1 sums over the first space and the N2 sums over the second space. So let me just, here is phi nu. So you dilate, we have a different dilation for the first one direction, a different dilation of the other direction. Okay? This is, so these spaces for the various, for instance, let me just say a few words here. If Q is 2 and S is 0, then these are the HP I wrote before. The multi-parameter, two-parameter triple HP space. When S is 0 and P is greater than 1, these are the LP spaces. When you don't have any smoothness. Now the multi-parameter Hardy spaces for P bigger than 1 are the LP spaces. Things are different when you go from 1 and below. So the multi-parameter HP spaces are not equal to the single parameter HP spaces, but for P less or equal to 1. But for P greater than 1, they are the same space and they are equal to LP. Okay. So what I want to do, we want to create frames on these spaces, and then we want to create to use wavelet based to decompose them, and then we want to do nonlinear approximation. That's the program. So the first thing I want to create the frames. We need to introduce dyadic cubes. These are the usual dyadic cubes. For each J, we have the set of dyadic cubes of side length 2 to the minus J on Rn. Okay, this is in one space. And of course, the usual, this is Xi is the lower left corner. This is the volume of each cube in Dj. And now, in our setting, we're going to talk about dyadic rectangles. Okay? So now we have our cubes are going to, our rectangles are going to be products of cubes One cube is going to be in one space, the other cube is going to be in the second space. One may have 10 dimensions and be small, the other may be 3 dimensions and very, very large. So that's how we play the game. This does not cover the case that you have parallelepipeds. You have 3 by 3 different dimensions. Because this is what you asked. If you have, instead of 2 parameters, then you need 3 parameters.
Yeah.
So
but it should in the end be the same.
the ideas are the same, yes. Okay.
So you,
Especially in approximation, this appears, it's going to appear in approximation, the number of parameters. So the more parameters they have, the worse is the approximation, the error of approximation, and it's getting worse. A logarithm term appears there, and it has to do with the number of parameters.
I'll slow you down a little bit while I'm still awake. So he's basically saying, why can't we just do R cross R? And then from there, we'll get everything. Why do we have to do N1, N2? Because we could always take all the...
I agree. I mean, in principle you can do it. In principle you can do it.
It would be conceptually simpler to see.
Yeah.
Maybe. I don't know.
In principle you can do it. I mean,
Is that what you were saying?
yeah. Or in the other extreme, you just take a general dilation matrix.
yeah, it's in Rn, different dilations needs. Yes.
The phi's are one of the determinant of the matrix.
one.
And then
Yes. Okay, I agree.
So, and then you have the smoothness spaces correspond to big smoothness. In all of this, then you have tensor products of one variable.
I'm not completely sure what you're saying. So you say you would like to do like a little Pele theory, let's say in 2D, but with a dilation matrix, which is...
No, I would say in general, they have a dilation, they have a block dilation matrix, which is a certain dilation in a group of variables and another dilation in another group of variables.
Sure.
You could separate it, then you have mixed smoothness with respect to all variables, essentially, right?
Yeah.
But the techniques should be the same. Because then you use tensor product structures with respect to the corresponding groups of variables. Either tensor products of one dimension, or here, tensor products of two slabs, and one dimension and 2 dimension. But it's essentially mixed smoothness concept.
Okay, so let me continue with. I agree. Let me continue with this is the usual Calderon composition. You start with this, with a pair of these functions that basically they satisfy this identity. This allows us. This is on the Fourier transform side, the same, this same property, and this allows you if we invert the Fourier transform, then we're allowed to decompose any function f with regard to these components. This is basically so. This is the spectrum decomposition of f. So. This on the Fourier transform side is supported on annuli around 0 basically. So from the size of this we can see we can actually get an idea why the size of this measures smoothness basically, because on the Fourier transform side the further you go, I mean when the Fourier transform goes decays polynomially, then this means smoothness somehow. And this is the size of this is relates to smoothness.
George, why here you are not taking 2 different J1 and J2 in this decomposition?
No, this is one. This is one. I'm going to go now to the multi-parameter.
Okay.
Now for the multi-parameter, the analog of this, for the multi-parameter, the analog of this is this. Okay. We have.
This was my question.
Yeah. Nu now is a multi-index. Okay. Nu1, Nu2. And of course, what we want to do here, we want to discretize the sum somehow. And for discretizing the sum, we introduce this notation. So for any rectangle I1 in the first space, I2 is a cube in the second space, we define GIX. So this is the this usual normalization factor. We dilate and translate with respect to the first variable, and we dilate and translated with respect to the second variable. And so this system, basically, it's easy to see that this system gives a frame, it gives a decomposition system, which on top of it is frame in the sense that you can characterize the norm of the spaces in terms of the coefficients. And by this I mean the following. First of all, I want to introduce, you expected that, I mean, we want to introduce the discrete analog of the spaces. So note that the smoothness S here, this is the inner product of S with N. S is a pair of numbers, okay? Is S1, S2, N is N1, N2. And, okay, now the definition, let me just mention that here there is no, for the triple Izotki spaces, we don't have P equals infinity. This goes back to, we have to work with BMO there and all the problems that appear. The definition would be different. You can work out the BMO, but the definition would be different. It would be unified. And of course, what one can show, what we have shown is that these coefficients. So usually you have these two operators. One is the analysis operator that takes a function f and it gives us the frame coefficients. The other is a synthesis operator. It takes a sequence in these sequence spaces, and then it builds up a distribution from these sequences. Now it turns out that both of these operators are bounded. First of all, SF is bounded from the best of spaces to the sequence spaces, and the synthesis operator is bounded from the sequence space to the best of spaces, and the same holds for a triple Izotki space. And moreover, the synthesis of these two, okay, if you compose the analysis operator with the synthesis operator, you get the identity operator. So basically, I'm talking about this. Okay, this is the composition of the synthesis and analysis operator. Okay, so let me continue with the theory. Now we have our spaces. Okay, we have our spaces, and we want to be able to do nonlinear approximation. The main vehicle there is to use wavelets. Why? Because they're bases, and then you can talk about inverse problems. I mean, you can talk about Bernstein inequalities, basically. Okay, so the usual case we're using Meyer's wavelet. Why Meyer's wavelet? Because they're infinitely smoothness. You can treat all the spaces with this set of wavelets, and they're supported on the Fourier transform side. They're compactly supported, and of course they decay. They decay exponentially. And okay, so we want to use what we're going to do. As you expect, we're going to use two wavelet bases. On Rn one wavelet basis, and to Rn two another wavelet basis, and then we're going to take the cross product. That's what we're going to do. And this is going to be our new basis. Okay, this is the normal thing to do. Let me just give you the notation. Okay, so this is on Rn. We don't have a single wavelet. We have a family of 2 to the n minus 1 wavelets that is constructed by the product. So this E. This set E is the set. I'm rushing a little bit because most of you know it's not. Yeah. So, but the set E is the number. Is the set of non-linear vertices, non-zero vertices of the unit cube. We have 2 to the n minus 1 of this. So its Hj here is an element of this form. Okay. It's a all these numbers are zeros or are ones. So if it's 0, we get 5. If it's 1, we get this one, and we're not allowed all of them to be phi's, basically. So you have to have one psi at least in one direction. So you get the 0 moments, and this set is the regular tensor product wavelet basis on Rn. So this is the most important properties of Meyer's wavelet. This is the smoothness. Okay, the support on the Fourier transform domain. You see they have all the zero moments. It has all moments are zero. And okay. Now, we want to talk about product wavelets on Rn1, Rn2. So I'm going to take two families. We're taking two families. Psi AI, EI here. I is 1 or 2. Okay, so we get one family. We get one family for this space and the other family for this space, and then we could take the cross products. So this is a typical wavelet function in the cross product. In this, the index E now, E is E1, E2. This is E. E1 is one of the corners, no zero corners of the vertices of the one cube, the others of the other cube. Okay, and okay, I believe this is clear. And of course, we expect to have this decomposition, which is indeed the case. It's an orthonormal base for L2, and moreover, we can characterize the spaces with respect to these coefficients. Okay, I'm not going to say anything more about this. This is all right. Now, the way you do that, you use what we call the almost diagonal matrices. So there's a standard way of dealing with these things.
I mean, this business with this E's is kind of following like multi-resolution analysis, because you have the phi's involved there too, as well.
Yeah, but
so this is kind of why can't you use in each group of directly hyperbolic bases? Like,
this here.
but only in two groups. But in each individual group, he has basis functions which go levelwise. That is that some of these products involve also the scaling function. You have a basis which is only wavelets.
But its size, don't they?
This is, but if you do it in Rn1, so in Rn, so I take this wavelet base on Rn. You can take any wavelet base you want on Rn.
Okay.
And then you take the cross product.
Yeah. Yes, the product is hyperbolic, but in each group you could have a very hyperbolic base.
You could, but what's more? What is that? You have two parameters. So in each one is regular, usual regular, and then you multiply.
Okay, let me continue with the nonlinear approximation now from product wavelets. So this work was initiated basically by a paper of Ron, Yaworth, and Popov. I remember in Journal of American Mathematical Society in '89. I remember that was. I guess that was a breakthrough. We can say that it was a breakthrough for that time. I mean, that was, of course, people in approximation, more or less. I guess you were expecting something like that or not. I mean, because we had the box. I mean, the free node splines. You were expecting anyway. You had work to do, but for people in approximation, that was more natural than for people in harmonic analysis. And then I wrote this number in these names here. Then there's a paper by Ron, Hotmuth, and Albert. You're doing restricted nonlinear approximation, where the nonlinearity comes from the volume of the cubes, basically. So you restrict the volume of the cubes you're using. And also Temnyakov did, Volodya did, were using some of his results. I mean, this he did with greedy algorithms. Okay, so the problem, the usual setting is the following. Okay, we have our wavelet basis, okay, and we want to approximate a function f in LP from a nonlinear manifold, for this non-linear manifold, meaning that we are allowed to use only the linear combination of m of these wavelet elements here. We can choose any m of them. And the question is find the one which realizes the best approximation, basically, find the closest one. And we want to measure the error in LP and HP for P less or equal to 1. Why HP for P less or equal to 1? Because for P less or equal to 1, we have the wavelet decomposition there. We have the frame decomposition for the HP space, not for the LP spaces. So okay, now, So our goal is to establish Sharp, Jackson, and Bernstein estimates in terms of the Bezoar spaces. Now the Bezoar spaces are the usual Bezoar spaces we expect. So we have our two spaces. One is tau is alpha plus 1 over p. As usual, this is the demarcation line along the limiting line of the Sobolev embedding theorem, where alpha, okay, is S1 over N1 in one space and alpha is S2 over N2 in the other case. So these two are the same. S1 over N1 is S2 over N2, okay, in the two spaces. And this is S1 and S2. So basically we have the line with slope N1. And these are the natural spaces we're going to use to measure smoothness. This is what Ron was telling yesterday. It's important to mention that we have two embeddings here, that these spaces are embedded we have in LP and HP. And also, this is the main results. I'm going to stay a little bit on this one. So the best, for p between 0 and 2, so we get the anticipated order of approximation. For p greater than 2, we have this logarithmic term. Now, because we have two parameters. If we had m parameters, here we have m minus 1. So this it would appear. I mean, 3 parameters. If I had R1, R2, R3, I have 2 here, 2 over this. Okay, this is the effect. I mean, so
3 halves.
Not wrong. I'm going to have the log would be raised to the third power and then times this. So the number of parameters minus 1. That's the power here. I'm not talking about 1/2 minus 1b.
Okay, but that log of m cubed is 3 log m, so why you worry about the 3?
Okay, let me.
The cube is outside the log. Is that right? It's logion cube.
Well, that's what I was asking, whether he got 3 halves or...
Log m
3 minus
1/2 minus 1b.
Times
And now you're saying that you have...
minus 1.
Times?
J minus
in the exponent.
When you have several
Shouldn't you-
parameters,
shouldn't
Oh, okay, here, yes.
parameters.
You have k parameters, k minus 1 here. Yeah, yes, this is what I'm saying. So this is where the number of parameters comes into play. So if I want to use parallelepipeds, different directions, so up here would be 3 minus 1, 2.
Now, do you think
this
that
is-
this
but
could
this
be
is-
improved? or-
No, this is exactly what I was asking you for. Because if you now go to many parameters, say if you distinguish between A, you are basically taking a full tensor product approximation. You are taking a full tensor product approximation. Now you take a sparse grid between 2 groups of variables. But if you just chose in each group of variables directly a hyperbolic basis, I think you may get for corresponding mixed smoothness even better estimates.
Better estimate?
Yeah, because you go in each basis, you go level-wise, right? When you look at a wave with group E, then all factors in this have the same dyadic level, do they? They have the same dyadic level. These are functions with the same dyadic level.
What is the number of parameters in your case?
Number of basis functions.
No number of parameters. You have like R cross R or what? In your case.
Yeah, I have a hyperbolic basis in one group.
Yes.
And a hyperbolic
You
basis.
hold on. You have more parameters there. Hold on. What?
I'm not so sure. It's just
No, here this is regular.
I suggest we just take R plus R.
Okay. No. Let me.
Take R
let-
times R. All right.
If you take R times R, this is what you get. R times R.
this is exactly the way. for-
Okay, so
for
let me just say the following. The key to proving, the important thing here that these are sharp. These estimates are sharp. You see, for the Bernstein estimates, the log term appears for p between 0 and 2. so it's on the other side. And these estimates are sharp. So it means that you cannot beat you need to have the logarithm. You cannot get away with this. And to see this, this is the basic lemma we're using. This is a lemma that I think it appeared, I have seen it in Ron's paper, but it appeared in Volodya, I think. Volodya.
I think this is Pfefferman-Stein.
I think it's Volodya did it. Temyakov, in a paper of his 1998, I think he has M-term greedy algorithm, something like that. That's why and Ron is using it also in this big paper, nonlinear approximation you're using this. So I want to show you this to see how the logarithm terms appear. Let me give you an example, an instruction. Let's assume that I'm going to give you a function f that this is equal to this, and this how you construct the sharpness of all the estimates. So let me split this. So let me define lambda j. So let's see. We live in the unit square. Okay, lambda j are all the cubes I, which is I1 cross I2, and the length of one side is 1 over 2 to the n minus j. I have an n big enough, and the length of the other cube is 1 over 2 to the j. Okay, so for, let's say, lambda 0 is all the cubes here. So let's say this is, I'm going to split it here. I'm splitting it here. So I'm going to have one direction is going to be 1 over 2 to the n, and the other is going to be 1. This is lambda 0. So lambda 0 are these rectangles. Lambda, how many of them we have? We have the area is 1 over 2 to the n is, so we have 2 to the n of them. You agree? So so the number of rectangles lambda 0 is 2 to the n. And of course, I mean, lambda n, what is lambda n? Lambda 1 is we double, we make it half in one direction, we double in the other direction. So lambda n is this one. So we have this one. And you see how so how many of them we have here? The same. We have 2 to the n. So all of them have 2 to the n. So the number of rectangles in lambda j is 2 to the n. What is the area of each one of them? Is 1 over 2 to the n. So they have, and okay, playing this game. So how many we have? So we have lambda 0 up to lambda n. We have n plus 1 layers. Okay, the last one is going to be this one. We go all the way to the other direction. And let me now define f. Let's define f. I guess you have seen it. It's easy to guess now. Let's define f of x. The sum j equals 0 to the n to let's this one. This one we define. Minus 1 over p. And here we have the characteristic on its side. I'm sorry. Sum, I forgot the sum over sum I and j.
But all the eyes have the same measure.
That's correct. That's correct. J equals 0 for n. This is f of x. And so if we want to see this, so it's the interesting thing here, so if we want to see the f of x, the norm, the LP norm of f, so this goes out, this is 2 to the np, and then we have this one, and this is the key observation that at each point, this is how many, at this point, how many layers? All of them. So this is n plus 1. You agree this is an approximation. So this is 2n over p times n plus 1. How many elements we have? What is m? What is our m? What is our m? We have m is n plus 1. And so think of lambda 0. How many elements we have lambda 0? 2 to the n. Lambda 1, 2 to the n, all of them. So we have n plus 1 times 2 to the n. Now, this is exactly this one. This is m1 over p log m 1 minus 1. So you cannot, and that's how you construct also a counter example that you can have a better approximation of using this type of idea. Okay, so and I'm finishing in 2 seconds. So, okay, then once you have direct and inverse theorems, you can define the K functional. The K functional, this is for a fixed f. The K functional basically is a function with respect to t. The K functions were introduced by Lyons and I remember and Peter to do interpolation for us an approximation. This tells us something more. So if this quantity is small for a function f, it says two things. First of all, that this quantity is small, so you can approximate f with a sufficiently small, smooth function. So this is small. However, you have some control over the norm of the smooth function, because this has to be finite. So it contains information contains more information. And so the direct estimate, a typical direct estimate is of this form. So you control the error of approximation from the K functional, and this is for p between 0 and 2, and this is for p, of course, between 2 and infinity. This is standard. This is standard way of dealing with these things. And of course, we have the inverse estimates that somehow you control the K functional. It depends of the norm of the approximation space here. Okay, this is unfortunately, as you see, the logarithm appears, so we cannot close the loop. We cannot characterize the approximation spaces completely in terms of in terms of the error in terms of the K functionals.
Except for p equal to.
Yeah.
Except for p equal to. Yeah, I agree. And is this the end? This is the end, I guess. I thought I had one more slide. Okay, this is it. Thank you.
So it's really left open still to characterize the approximation spaces for hyperbolic.
But you cannot. You did something with hyperbolic, but it was linear, I guess. It was linear. You see what I'm saying? With Koniagin, I think, and Temnikov. You did something, but you did.
But why do you say?
You're saying
approximation spaces.
You're saying it's open, but we have the results are sharp here. You cannot do anything.
Yeah, but it says that the right spaces are not these Besthoff spaces.
Oh yeah.
And not the Triple-Lizorki. There's some other crazy space that you have to, for which you have the Jackson and Berenstein. Was the expert at Jackson and Berenstein. He's embarrassed by that fact.
What would be the other space?
Hasn't found out what the correct space is.
You cannot find this space.
Huh?
You cannot find this space.
Oh, come on now. That's because I'm getting old. But if I were only 70, I would have them by
I'm talking
72.
about anybody, not only you. This is forget it.
I don't know.
Well, in
Here we
10
want
years,
to see exactly what we
next
got,
one.
exactly
For the next one.
the sharp estimate. This is what the point was here. What are exactly the estimate that you have?
Well,
How the logarithmic terms appear exactly?
no, but I mean, what you're saying is if you're interested in looking at the error of approximation in HP, and you want to measure the error for functions in the Besthoff or so forth, this is M to the whatever, and the log may or may not appear, you have, this is it. That's it.
That's right.
But if I say to you, yeah, but maybe don't put best off there, put in the curiosity spaces. They're a little different. Maybe you'll get,
Okay.
massage
Maybe,
a
okay.
little bit.
Theoretically, it is possible, of course.
I mean, the idea was if you want to use hyperbolic bases, you have to go to product space. That was the first idea. You have to go to product space. You cannot deal with the regular one parameter spaces. But then we ended up with
This is important and difficult. They have the same thing right with these sparse grids. They have powers of log, but we're not sure
It's the same.
as sparse grids whether they should
And they should
quite be this. Well, they should be. What do you mean? They have some cases where they're not.
They do not go into inverse. They go into inverse. They don't have space characterization.
No, but sometimes they have the mixed norm total of space,
Yeah.
and then you can say, well, what is the entropy or whatever of it? And I think they missed the law.
Well,
Maybe wrong.
by the way, there's a huge problem here to characterize that, using the maximum operator. This is true, but there is no.
this is not done.
There is proof.
Even Gandhi.
That's what I'm saying.
So how do you define the Hardy spaces? You define
We
them-
define here with F02. That's what.
You
That's
define
what
it as horizontal spaces.
So, I see. You define them that way.
Yes.
So it's like a totality.
Yeah.
But
They have atomic decomposition, which is the atoms are very, very strange. They are not the regular atoms. But maximal characterization, I mean, there is in the case of the
Polydisc. In the case of
the
polydisc.
polydisc, I mean, with complex method, Stein and Gandhi, they have this. But for the real, there's no proof. This is a huge problem. And this is where we started from. But we could not solve that problem. There's a very, very interesting problem.
Okay.
good. Yeah.
Okay, thank you very much.
Thank you.